Hello, welcome to our course on Introduction to Cryptology. Today is week 1 lecture 4. Today we will cover the idea of perfect secrecy introduced by Shannon. But before we do the idea of perfect secrecy introduced by Shannon, we have to recall a bit of probability theory. So, we assume that you know basic definitions of probability and all that. Now, we also know that a cryptosystem is specified by the 5 tuple PCK-ED. Now, what happens is that suppose Alice is sending a sequence of letters taking from P, which is basically a part of a language. So, suppose Alice is sending x1, x2, x3 and so on, xn and so on, where each xi belongs to P. Now, each time Alice sends an element from P, we can imagine that it is an outcome of a random experiment. So, we can associate a random variable related to the associate a random variable to those plain text symbols. So, what we will do is that we will say that there is a random variable x associated to P. So, x is a random variable associated to the set of plain text, and each time Alice sends a plain text letter, we get an instance of that random variable. So, this is what I have written here, that assume that it is possible to define a probability distribution on the plain text P, and x is the random variable corresponding to the plain text. So, with the random variable there is of course a probability distribution. So, we can talk about things like this, that what is the probability that the random variable capital X takes the particular value small x, where small x is inside P. This probability will typically depend on the language that Alice is using and the encoding of that language to the plain text symbol strings. On the other hand, Alice also chooses a key and transfers the key through a secret channel to B. That key is chosen from the key space, which is denoted by script k. Each time Alice wants to send encrypted message to Bob, she has to choose a key. That key is also associated to a random variable, because Alice is choosing the key in a randomly from the key space. So, we associate a random variable capital K with respect to with the key space k, and of course, it gives the probability that a particular key is chosen. So, suppose a particular key small k is chosen, then we will write the probability of that choice as this one, probability of k equal to small k. And now, we know that encryption function is a function which depends on small k, that is the key, and x, that is the plain text, and I write like this y. So, in a way y is also an instant of a random variable, but that random variable's distribution is dependent on the distribution of x and k. So, I will write y, a random variable associated to the ciphertext y, ciphertext in C. So, if you look at the slides, I have written those things formally. So, we say that assume that it is possible to define a probability distribution on the plain text space P, the key space K, the probability distribution on P and K induces a probability distribution on C. Let the random variables associated to plain text keys and ciphertext be x, y and k, that is exactly what we have discussed before, and the probability that capital X, that is the random variable, is equal to small x is denoted by probability capital X equal to small x. The probability that capital X is equal to small capital K is equal to small k is denoted by probability capital K is equal to small k. Probability that capital Y, that is the random variable corresponding to the ciphertext, is equal to y, small y is denoted by probability of y equal to small y. Now, we have assumed here that there is a probability distribution on the set of plain text, and we know the random variable corresponding to that, that is x. We have assumed there is a probability distribution on the key space, and there is a random variable corresponding to that, that is capital K, and we know that x and k determines y. So, the question is what is the probability distribution of y, and here we have that. Let me explain that to you. Yes. So, first of all we have to consider a set C k which is E k x, where x runs over the set of plain text. So, this is the set of all possible ciphertexts given a key k, that is we choose a key k and then suppose x1, x2, x3 and so on up to x capital M are the plain text elements, suppose all the plain text elements. So, what I do is that we take the encryption x1, encryption function with respect to k of x2 and so on up to E k x m, and then we put that within a set symbol, and this is going to be my set C k. And now the probability distribution of ciphertext is probability y equal to small y equal to summation. Now, this is a product of two probabilities, probability k equal to small k into probability x equal to dky, where k runs over the set such that y belongs to C k. So, we have to take all the C k's in which y belongs, of which y is an element, and take that k and sum this over all those k's. Now, let us try to see what happens here. So, let us take the left hand side of this equation, that is probability of capital Y equal to small y this is equal to, now we will always have a key. So, I have a key probability that there is some key k and this intersection, the event that we are getting y from the x. So, for a given k inside the key space, if I find that there is an plain text whose encryption is y, then I know that I will get the encrypted symbol as y, and we have to sum over all possible k's, and here of course that if there is no y corresponding to that k, so I will not take that. So, I must have at least one x for which I get that y. Therefore, we have to vary k in such a way that y is inside ck, and now we assume that the choice of the cipher choice of the key and the choice of plain text are independent. So, we write another step here. So, k equal to small k intersection y equal to ekx is same as x equal to dky. So, I know that these two events must occur together to get y, and then I have to vary over all k, and I know that, or I assume very reasonably that the key and the plain text are independent. Therefore, this can be replaced by a product. In fact, I should write this as I should write this in this way, that it is capital X equal to small x equal to dk y. I should write like this. So, here I have got this. So, please read that it is capital X equal to small x equal to dk y. Now, so that is the probability of y y equal to y small y, and then we have another probability over here, that is a conditional probability, that suppose we know that x is equal to small x, then what is the probability of y being equal to small y, and that is exactly the probability that you have a k such that dk y equal to x. So, sum over all such k's, we do that, if we sum over that we get this conditional probability. Next, now we can use whatever we have learnt to obtain an expression of a very important conditional probability, which is probability of capital X equal to small x given that capital Y equal to small y. What we know is, we know probability of capital Y equal to small y given capital X equal to small x, that we have seen before, and we know the probability of capital Y equal to small y. What we do is that we use the basic definition of conditional probability. Here probability of capital X equal to small x given y equal to small y equal to probability of capital X equal to small x intersection y equal to small y divided by probability of y equal to small y, and this one we can write by using the definition of conditional probability as this: probability of capital X equal to small x into probability of capital Y equal to small y given x equal to small x, and we divide it by y equal to small y. And now we go back to our previous expressions. Here we have the expression for probability of y equal to small y, and we have the expression for probability of y equal to small y given x equal to small x. If we plug in those things, we get this expression probability of capital X equal to small x into the sum, which is equal to this thing, and in the denominator we have the other sum that we have discussed in the previous slide. So, this is the probability that capital X equal to small x given y equal to small y, and once we have this expression, we can we are closer to discussing the concept of perfect secrecy as proposed or as initiated by Claude Shannon. But before that, we will take a small crypto system and see how to calculate these probabilities. So, now we have a small toy crypto system. So, what we have here is that we have the set of plain text having two elements A and B, and set of keys having three elements K1, K2 and K3 with the probabilities. So, we know that probability of x being equal to A is 1/4 and probability of x equal to B is 3/4. Probability of k equal to K1 is equal to half, and probability of k equal to K2 equal to probability of k equal to K3 is equal to 1/4 as we have written here, and the cipher text consists of 4 elements 1, 2, 3, 4. Now, we can represent the crypto system that we have formed in this way. So, if you look at this table, there is on the horizontal side, that is the columns are marked A and B, and rows are marked K1, K2 and K3. We should read like this, that if I choose the key K1, then if my plain text is A, then my encryption is 1. If my plain text is B, then my encryption is 2. If I choose K2, if my plain text is A, then my encryption is 2, and if my plain text is B, then my encryption is 3, and so on. Now, let us look at this slide. Here I have written down the crypto system over here and the related formulas over here, and we will derive the particular values over here. So, let us see what happens. So, suppose I am asking what is the probability that capital Y is equal to 1. So, I am asking what is the probability of capital Y is equal to 1. For this, we can invoke the previous formulas, but we can just see that from the table whether we can understand this. So in this body of the matrix, we try to find out where is 1 is over here. So, that means there is only one situation where I get a cipher text 1, that is when plain text is A and key is K1. So, we can in fact forget all the formulas that I have discussed just before this, and write the and understand that I get cipher text Y equal to 1 if key is K1 and plain text is A, and never otherwise. So, therefore, I will write like this: this is the probability of getting k equal to K1 and probability of getting x equal to A. Probability of getting k equal to K1 is given over here, which is half, and probability of getting x equal to A, which is given over here, which is 1/4. So, I get 1 by 8. So, which I have listed over here. Now, I can question that what is the probability of getting y equal to 2. Of course, if you patiently go back and see the formulas that I have discussed, you will be able to do that. Then you have to talk about the C case and all those things, but basically for working we can do otherwise. So, what we can do is that we can say that where I am getting 2, I am getting 2 over here and 2 over here. What is the case of what is this case? We are getting 2 because we have key equal to k1 and we have plain text equal to b, and here we are getting 2 because we have got k equal to k2 and plain text equal to a. So, these are the two cases. So, we are getting when the plain text is b and key is k1, we are getting 2, and when the plain text is, let us see, the plain text is a and key is k2, then also we are getting 2, and that these are the only places we are getting 2, and these events are mutually exclusive, and I am writing this probability as product because we are assuming that plain text and cipher text they are independent. And now we put the probabilities over here. So, x equal to b is 3 by 4 and k1 k equal to k1 is half, and x equal to a is 1 by 4 and k equal to k2 is going to be 1 by 4. So, I have got 1 by 16. So, I have got 3 by 8 plus 1 by 16 is exactly what I have got here, and you may check that it is 7 by 16. Now, we can calculate all these probabilities in this way. Here I will show here, because that here we have to use something else. Now, suppose I have a situation where I want to find out the probability of x equal to a given y equal to 2. Probability of x equal to a given y equal to 2. So, what is this? Now, this is, if you look at this formula, use this one, this is probability of x equal to a and then probability of y equal to 2 given x equal to a, yes, and then divided by probability of capital Y equal to small y. Now, I know what is probability of x equal to a, that is 1/4, and I know that what is probability of y equal to 2 given x equal to a. What is that? Given x equal to a, y equal to 2 if k2 occurs. So, this is probability of getting k2. Probability of getting k2 is 1/4, and probability of y equal to 2, here this is 2, probability of y equal to 2 is what? We have computed that is 7 by 16, 7 by 16. So, this gives us 1 by 7. So, these conditional probabilities can be computed in this way. This leads us to our last topic of this lecture, that is perfect secrecy, or this is the topic to which we are driving at. The idea of perfect secrecy was formulated by Claude Elwood Shannon around 1948. He stated that a cryptosystem has perfect secrecy if probability of x equal to x given y equal to y is equal to probability of x equal to small x for all x inside P and for all y inside C. if you look at this crypto system that we have seen, we see that probability of x equal to a given y equal to 2 is 1 by 7, whereas probability of x equal to a is 1 by 4. Therefore, it proves that it is not perfect, it does not have perfect secrecy. But if there is a crypto system for which this is true for all x and y, then it has perfect secrecy. And now the example of such a crypto system. Interestingly, such a crypto system is shift cipher with a condition. Now let us read. Suppose that 26 keys in the shift cipher are used with equal probability 1 by 26, then for any plain text probability distribution the shift cipher has perfect secrecy. How do we prove that? We can prove that, and let us look at this line and the following lines. We start with y equal to small y, that is equal to k running over z by z sub 26 probability of capital K equal to k into x equal to dky. This is exactly the formula that we have derived. Now our assumption is that keys are chosen equiprobably, that means there is no bias. If there is no bias, then probability of k equal to k is 1 by 26. I take 1 by 26 out, so I get something like this, and now I am varying k over z sub 26, but y is fixed over here. Therefore, y minus k modulo 26 is going to vary over the whole space, and therefore this probability is going to sum up to 1. So, I have 1 by 26. On the other hand, if I consider probability of y given probability of given x equal to x, then that is probability of getting the key y minus x mod 26, which is 1 by 26, because each key is chosen equiprobably. And now we see the conditional probability formula, probability of x equal to x given y equal to small y, that is this probability of x into probability of y equal to small y given x equal to small x divided by probability of y equal to y. We know probability of y equal to y is 1 by 26, this is 1 by 26. So, we end up with probability of x equal to x. So, we have probability of x given x equal to x given y equal to small y equal to probability of x equal to small x, and that is perfect secrecy. So, summing up, in this lecture we have studied probability distributions related to plain text, keys and ciphertext, and we have studied the idea of perfect secrecy introduced by Shannon, and finally we have studied the condition under which shift cipher achieves perfect secrecy. And now I go back to the last slide of my previous lecture, where I said that do not underestimate classical ciphers. Shift cipher is the first cipher that we study. When we study shift cipher, it seems that it is too simple, it cannot have any security, but very soon we see that shift ciphers can have perfect secrecy, but with one condition, that each time you encipher a plain text, you have to choose a key equiprobably from z sub 26. So, that is the condition, and that is a very difficult thing to achieve, but nevertheless it is provably secure if we have the condition. So, this is the end of today's lecture. We will continue discussions on cryptology in our subsequent lectures. Thank you.